Hello and welcome to Lesson 2 of Module 4, Unit 8. This is our introduction to quadratics. What we're going to be, or a continuation into our quadratic unit. What we're going to be doing in this lesson is we are going to be taking what we've seen in previous units with transformations, and we are going to be applying them to our new parent function, which is our quadratics, and also adding into like identifying pieces that again we've seen in previous units before. So first of all, a little bit of review from from lesson 1. The name of the function to the left is called a quadratic. And our parent function is y equals x squared. And it creates a U shape, and that U shape is called a parabola. Now, we have pieces of information that we've seen on here before. We have our x-intercepts, which are -1, 0 and 3, 0. We also have our y-intercept where we cross the y-axis. That's going to be 0, -3. Finishing with, oopsie, sorry, did the color. Let's try green. Our vertex, that's going to be either our minimum or our maximum. And our vertex here is 1, -4. And this is our minimum, and that's because our graph is decreasing to increasing. It's our lowest point. Now, we do have this new word. It's called an axis of symmetry. It is a line that cuts our graph perfectly in half. What happens is that whatever happens on one side, so this is 2 away from the axis of symmetry, happens on the other side. It's 2 away. Whatever happens on one side has to happen on the other side. That is what an axis of symmetry is. Now, because it is a line, it has an equation. And so it's going to be x equals 1 for this problem. The reason it's an x equals is because it's a vertical, undefined x equals. It's a VUX. And so what we're going to do is we're now going to kind of take that information and what we saw in our previous lesson, and we are going to apply it to our parent function. So our parent function is f of x, also known as y, equals x squared. So here's x and y. We have -2, -1, 0, 1, 2. And what happens is we square them, so we get 4, 1, 0, 1, 4. Now, if you forgot, the reason that they are now positive is because a negative times a negative is a positive. And so we're going to graph these points. We got -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And then I'm going to connect these points. Now, again, be careful when we connect them, we want to make sure our graph is curved. It's not an absolute value V-shaped graph. So there's our function. Now what we're going to do is we're going to write our axis of symmetry and our vertex. Now personally, I like to write my vertex first. It is the point. It is either your minimum or your maximum. And so in this case, our vertex is the origin, and it's going to be a minimum because it's our lowest point. From there, our axis of symmetry we can find because our axis of symmetry will always go through our vertex. And so that's why I like to find it first. It'll always be the x value of your vertex. Now, we do use a dashed line kind of similar to an asymptote. We use it as a guide for our graph, but it's not part of the graph. And then we're just going to find some other pieces. Our x-intercept, we only have one. It's the origin, which is also our y-intercept. Our domain for this will always be -infinity to infinity. And our range is going to be bracket 0 to infinity. Again, the reason for that bracket is because we hit at the origin. Now, there is a pattern. It's our perfect squares. Perfect squares. And so that means we go over 1, up 1, over 2, up 4. And those are the last 2 points of our parent function that we're going to be using to graph today. But before we do that, we're going to kind of talk about our functions and look at our function a little bit more. So this should be repetitive. Our A value is our vertical stretch or shrink. If A is negative, that means it's a reflection over the x-axis. Now, what it also means from yesterday is that it is concave down. And so, what our graph would look like if we have a reflection, it's going to be a sad face. And then if our A value is positive, there's no reflection, but we can tell that it is concave up, and it's a happy face. Okay. We also have our H and K values, which are the same. This is going to be your horizontal shift, left and right. And then your K value is your vertical shift up and down. Now, this does have a fancy word, this vertex form. It's because it tells us our vertex. Our vertex is H, comma, K, where, like our absolute value, H is opposite and K is the same. Now, once we have our vertex, we can find our axis of symmetry, which is x equals h. It's the point, it's the x value of the vertex. Okay. So now that we know that, if we're given our vertex, we can actually write the equation because we're kind of going to work backwards. So we have our vertex, we have h and k. So we just have to remember that when we plug it into the equation, we're going to change the sign of that h value. So that's how we get y equals x minus 3 squared minus 1. Now for number 2, we're going to change that sign. Now, we don't really need that plus 0, so what you're going to see when this shows up is just y equals x plus 4 squared. For our next one, number 3, minus 0 plus 6, well, x minus 0 or even plus 0 doesn't do anything. And so what this would look like if I asked you to graph it would just be y equals x squared plus 6. There would be no parentheses. And our last one would be y equals x plus 2 squared minus 4. Okay, so for number 5, what we're going to be doing is we're going to be given a graph. We're going to identify all these pieces. So again, I personally like to find my vertex first, which is going to be 1, comma, negative 9. Our axis of symmetry is the y value of the vertex. And so here is that axis of symmetry. Our vertex is a minimum because it's the lowest point. So what that means is our graph is going to be concave up and our A value is going to be positive. From here, our x-intercepts are going to be negative 2, comma 0 and 4, comma 0. That's where we cross the x-axis. And our y-intercept is where we cross the y-axis, which is going to be 0, comma, negative 8. Our domain, remember, quadratic is always negative infinity to infinity. And our range, what's really cool, and this showed up in absolute value transformation, is that the y value will be part of our range, and because there was no reflection, it's going to be negative 9 to infinity. How we find our A value. You look to see how far over we go, over 1. How far up do we go? 1, that is your A value. And so, now that we have our vertex and our A value, we can write the equation of this function. So y equals our A value, which is 1. X, opposite sign, x minus 1 squared, same sign, minus 9. Now, we don't really need to write that 1, so what we should have for this final answer is y equals x minus 1 squared minus 9. There's your answer. Okay, I'm going to pause the video, and I want you to try number 6 on your own. Okay, hopefully this is what you got. Here we go. Vertex, negative 2, comma, positive 8. Axis of symmetry is x equals negative 2. It is a maximum because it is the highest point. Our x-intercepts, we have 2 of them at -4, 0 and 0, 0. Our y-intercept is our x-intercept, which can happen. Domain, as always, -infinity to infinity. Our range, because it's a maximum, that means our a value is going to be negative and it's concave down. Our range is going to flip, and so it's going to be -infinity to the y value of our vertex, so 8. Now, how do we get our a value? We go over 1. How far down, or in this case, down did we go? -2. And so we need that because our equation is going to be y equals -2x plus 2 squared plus 8, because we're changing that sign. Okay? Let's go to the next page. So we're now going to actually graph these problems. There's 3 methods to graph. Your first one is your tried and true one. We saw them in our last, unit. So I'm going to describe our transformations. This should be second nature to you by now because it's the same thing. So it's a horizontal shift, right 3, and a vertical shift up 1. And so we're going to start with our parent function values. And remember, it's an x squared. So -2, -1, 0, 1, 2. We get 4, 1, 0, 1, 4. Now we're going to drop in our transformations, and we're going to add on both sides. So we would get 1, 2, 3, 4, 5. And then adding 1, we would get 5, 2, 1, 2, 5. Now, the nice part, the cool part about this is that your vertex will always be that middle point of your table. So 3, 1, and so our axis of symmetry is going to be x equals 3. We can write our domain right away. We can do a lot of stuff without even graphing. That's kind of cool. Domain is -infinity to infinity. And our range, because our a value is positive, it's concave up, it's going to be bracket 1 to infinity. Remember that this value will always show up here, the y value of your vertex. So let's graph our points. 1, 5, 2, 2, 3, 1, 4, 2, and 5, 5. And so when we connect them, what should happen is that if we draw in that axis of symmetry, what happens on one side happens on the other. And it does. Okay, so that's your normal method that we've seen before. The second method, it's one of my least favorite ones. It requires a calculator, and I personally think a lot of work. So we can still describe our transformations. We have a vertical stretch by a scale factor of 2, because that 2 is on the outside. Then that +4 is on the inside, so it's going to be that horizontal shift left 4, finishing with that -1 on the outside, so that's going to be that vertical shift down 1. Now our vertex is going to be -4, -1, and so our axis of symmetry is x equals -4. What you do is you plug your vertex in the middle of your table. You then find 2 more points that are greater than or less than. So I'm going to go greater. And what you do is you plug them in to your function. So 2 times -3 plus 4 squared minus 1 is 1. And then you find f of -2. So 2 times -2 plus 4. Now, technically, we should have extra parentheses because whenever we replace a variable, we should have parentheses. So 2 squared is 4. 4 times 2 is 8. 8 minus 1 is 7. So the reason that this method works is because of what we saw in our table. We can now reflect these points over our vertex to get our y values and then just go backwards, so -5 and -6, to fill out our table. I told you, least favorite method. So we can now plot these. -6, +7, negative 5, positive 1, negative 4, negative 1, la la la. There we go. And then when we connect them, we get this graph. And so why we can do this method is because what we're doing is we're reflecting them over our axis of symmetry, which is where our vertex is. And so just to finish up, our domain, as always, is negative infinity to infinity, and our range is going to be negative 1 to infinity. If you haven't figured out yet, that vertical shift, that outside number, will always be in your range somewhere. Okay? Now, your last one, my favorite one. This is where all you have to do, identify your vertex, and then take your perfect squares and multiply by your a value. So our vertex, we're going to do this with the one above, is negative 4 comma negative 1. This means our axis of symmetry is x equals negative 4. So let's graph that real quick. Negative 4, negative 1, and our axis of symmetry. Our a value is 2. So what you do is you take your two perfect squares. This is coming from your parent function value. It's coming from the 2 points below your parent function, okay? And what you do is you multiply the y values, just the y values, by that a value. So we're going to multiply by 2. So we get 1, 2, 2, 8. The reason that we're multiplying it by the y values is because that a value would be a vertical affecting our y values. And so all you have to do is take these points and you graph them like that vertex was an origin. So what I mean by it, 1 over 1 up to reflected over my axis of symmetry. How I did that, I'm 1 away from the axis of symmetry. I'm going to go 1 away on the other side. Going back to my vertex, I'm going to go over 2 up 8, and I'm going to reflect it over. So again, 1, 2, 1, 2 on the other side. I can now connect my points with arrows, and look at that. They're the same exact answer, just way quicker. Okay. So let's do some practice. I am going to show you how quick the shortcut method can be. So our vertex, negative 3, comma 4. Our axis of symmetry then is x equals negative 3. Domain, negative infinity to infinity. Since our a value is negative, that means it's going to be concave down. So our vertex is a maximum because it's the highest point. And so our range is going to be negative infinity to 4 with a bracket. Okay, so let's graph that point. Negative 3, comma 4. Then I'm going to take my a values and multiply by negative 2. So 1, 1, 2, 4. Multiplying just those a values will give us 1, negative 2, 2, negative 8. So I'm going to go over 1, down 2, and now we're going to draw in the axis of symmetry to help us with our visual. And I'm going to reflect it over. Now going back to my vertex, I'm going to go over 2, down 8, and reflect it over to get my graph. And it's as easy as that. Okay. Let's do number 11. We'll do 11 together. So for this one, our vertex is, what is going on? Oh no, there we go, okay. 1, comma 3. So our axis of symmetry is x equals 1. Domain, negative infinity to infinity. Our range, because our a value is negative, that means our graph again is concave down. So our vertex is a maximum, and so we're going to be negative infinity to 3 with a bracket. And so when I plot that 1, comma 3, right there, here's my axis of symmetry. Now what I'm going to do is I'm going to take 1, 1, 2, 4, and I'm going to again multiply them by my a value. So I get 1, comma negative 0.5, 2, comma negative 2. So when I graph them, I go over 1, down a half, reflected over. Over 2, down 2, reflected over. I have 5 points, which is what we need, enough to connect them to create our graph. Okay, I'm going to pause the video. I want you to try the evens, 10 and 12. Okay, we'll go over them in class together, but what we're going to do now is we're going to move on to 13 and 14. So for these problems, all you're doing is given the graph, write the domain and range, or given the function, write the domain and range. Well, domain is always, no matter what, negative infinity to infinity. Our range, you have to see if it's concave up or concave down. This one's concave down because our a value is negative. So using that 5, it's going to be negative infinity to 5 because that 5 is going to be the y value of our vertex. Why don't you try 14 on your own? Okay, what you should have got, because our a value is positive, is we're going to have negative 3 to infinity because that vertex is going to be a minimum. Okay. Number 15. So what we do here is we create a quadratic function with a range of of 10 to infinity. So what this means is our graph is pointing up because bottom of our graph is at 10 to the top to infinity. And so our bare minimum for this, because our a value is positive, is x squared plus 10. The x squared is to let us know it's a quadratic, and the plus 10 is to know it's vertically shifted up 10. You could write it like y equals 2 times x minus 3 squared plus 10 if you want to be fancy, but you don't have to, but that is one way. Okay, I want you to try the next 5 problems on your own. I'm going to pause the video. Okay, let's see if you got them right. Here we go. So we have it going to negative infinity to negative 4. So our equation, our bare minimum for this would be y equals negative x squared minus 4. Again, you can be fancy and write negative 2 times x minus 3 squared minus 4. You just need that negative and that minus 4 in your problem. Our next one, it's concave down, so that means our a value is negative, and a vertical shrink of 1/2. So the bare minimum you need is y equals 1/2 x squared. But again, you can be fancy and write it as negative 1/2 x plus 2 squared minus 4. You only need at least that negative 1/2 to create that concave down and that vertical shrink of 1/2. From here, we have our vertex, we have our h and our k, and we have that it's concave down because of our range. So we would get y equals negative x opposite minus 9 squared, same plus 3. Again, if you want, you could add that like 2, a 1/2. Doesn't matter as long as that a value is negative. 19, we have our axis of symmetry. So this is going to be the x value of our vertex. It's concave up, so that means a is positive, and it's up 2, so our k value is 2. So what we have is y equals parenthesis x plus 4 squared plus 2. You can add like a 3 or a 1/3, your choice, but you need to have at least the red. And then our last one, number 20, we have our axis of symmetry is 8. We have a vertical stretch, a parent function shifted down 3, and a concave down. And so what we would have is y equals negative 2. The negative is for the concave, the vertical stretch by 2. And then we have x minus 8 squared because of our axis of symmetry, and then down 3. That is the only answer accepted for number 20. I hope you got it. What we're going to do now is we're just going to do a couple of things on our other packets. So here we go. This one. This is the table you should have It's been passed out, but if you need a new one, they're up at the front. Here we go. So our parent function is -2, -1, 0, 1, 2. We're going to square everything. And so when we graph it, here's our parent function. And so when we connect it, we want to make it that U shape with arrows on both sides. And then we're going to have our axis of symmetry go through it. And that's going to be, in this case, x equals 0, but it's going to be x equals h. We then have our vertex, which is h comma k. Oh, I guess I didn't write this. And our domain, -infinity to infinity, and our range is bracket 0 to infinity. So there's all those pieces for this blue piece of paper. And then there's one new blue piece of paper to finish off all of our transformations. Here we go. So the negative goes here. Boom, boom, boom. This is a reflection over the x-axis. We then have our A value, which this is our vertical stretch. So that's if A is greater than 1. Shrink if A is between 0 and 1 by a scale factor of A. And then we have our H value, which is inside. This should almost be second nature because we've written it so many times. It is a horizontal shift left. Ooh, whoa. Let's try this again. Left or right. And then finally, our K value, which is our last box. It goes here. This is our vertical shift up or down. Okay, I'm going to add a couple things. We have our graph that looks like this. We have our vertex, which is h comma k. We have our axis of symmetry, which is our AOS, x equals h. And then we can find our range with our k value. It's either going to be bracket k to infinity. If it's a reflection, so if it's -a, it's going to be -infinity to k with a bracket. And then our parent function values are -2, -1, 0, 1, 2, 4, 1, 0, 1, 4. If you ever need them. Voila! Okay, if you have questions, please let me know. Otherwise, I'll see you in class.